Okay, on the exam, the scores were not as good as they were on the last exam by a fair amount, probably about 10 points difference in the class average. So then I curved the score, and that's why your score doesn't necessarily, whatever you have minus something, you ended up better than that. So a couple of you just came in. So let me get those to you, Haley. And then I'll talk about a few of the problems. Oh yeah, I have yours. I'm not sure.
I can get it from you after class.
Okay. It must have got in another pile. Oh, there it is. So as usual, I will discuss a few of the problems that are more commonly missed. And unfortunately on this test there were more of those. That needs to be just a little bit further back. They're going to get a nice close-up of my ear there. So let me remember here. First page went pretty good for most people. The one about in a large city, 2 newspapers. Remember, that was one that was straight off of the review sheet, but I changed it slightly to ask a different probability problem, but with the same numbers in there. But part A says, what proportion of the city's households subscribe to the daily news given that they subscribe to the Globe News? And I just happen to be looking at version B, but if you're in the other version, I think I reversed it. Yeah, Globe given daily. So yours would be flipped around. But that's, by definition, that's the probability that they both occur divided by the thing you condition on. Right? Now, I thought I was giving you a really easy problem here, and an awful lot of you tried to make it hard, though, because you like hard problems. Right? What's the probability of daily and Globe? It says right in there that this percent of people subscribe to both. So that's all you had to do, right? What is that number? 0.1. Yeah, 10%, so 0.1. And then divide by the probability of the Globe, which is 0.25. If you're on the other version, you'd have the probability of D down there instead of the probability, but it's still the 0.1 in the top. Right? Now, there's a whole bunch of people who got lucky because I inadvertently did one thing. They did this. They had all this correct. Then they said, well, that's equal to the probability of D times the probability of G. Right? Is that right? Well, the correct answer to that question is, it might be. Might be if what? This is okay to do if what? If they're independent. And this one, they were independent. So it worked. But what happens if you do this? Well, you end up with a 0.1 times a, what is it? Not a 0.1. A 0.4 times a 0.25. I don't know. But it ends up canceling out and you get the same answer. So you're okay. But recognize, don't ever do it this way unless you're sure they are independent. It should be the probability of G given D. Right? That's the multiplication rule. And this one you didn't have. You could solve for it. Some of you did it that way. But I meant to make it easy so you didn't have to do all that. Okay, so that's that problem. Let's see. Off the first page, that's really the only thing that was real commonly missed. Second page had a normal probability problem. So that went okay for most people. Where people missed more commonly were the problems that had to do with the inverse norm function. So this version asks for the 85th percentile, so I call that P85. That's inverse norm of what? 0.85. Because the inverse norm function is a percentile function, so you just enter in directly. And then whatever the mean was, and whatever the standard deviation was. Right? And I believe it was 3,900 and 360. The other version asked for which percentile?
25th.
25th. Okay, so you put a 0.25 instead of a 0.85, but same numbers there. Okay, so this answer was 4273. 0.1. A lot of people rounded that off to the nearest whole, which I'm perfectly fine with, because when you're talking about grams, having a baby's weight to the nearest tenth of a gram is probably not important, so it makes sense to round that off. But then the next problem says find two scores that contain the middle 50%. All right, so if you draw a picture, you want the middle 50%. Which is going to be inside of the two dotted lines at standard deviation, because they would be 68%. So if there's 50% in the middle, what would this percentile be? In other words, how much area is there? 0.25 and 0.25 up there. Right? So it's always take the area, half the leftover area is in each tail. So this is P25 and P75. And then you find those just like you did here, subtract, or don't subtract them, but those are your two answers. All right? If you're on the other version, it asks for the middle, what, 60%? So then you would have 20%, 40% left over and 20% in each. So you'd have 80 and 20 to get the middle 60. Now there were a few people that got pretty good partial credit, but not all the credit that did. I'm not sure anybody did this exact thing, but middle 50%, and they found P05 and P55. How much area is in between those two numbers? 50%. But is it the middle 50%? No. It's shifted off, right? P55 is just barely left of the mean, or right of the mean. So this is 50% in between, but it's not the middle 50%. To do middle 50%, you have to find half of the leftover area and put it in each tail. Okay? Probably the most commonly missed problem on the whole thing was the one about the insects and whether the insecticide kills or not. What kind of a problem is that? That meets the conditions for binomial distribution. Okay? So I saw not a lot of people, but enough people that it concerns me that threw the normal CDF at that. Right? They went, oh, normal CDF, something, something, something. Right? Well, I don't know that I ever said this before, but if you tried to use the normal CDF, then you wouldn't have all the numbers, right? All the numbers you needed wouldn't be there. So if you ever find yourself making up numbers to stick into a function because they aren't, then you got the wrong function. Right? So recognize it's binomial, and then probability of x equal to 2, x exactly equal to 2, would be binom PDF. And then depends on your version as to how many insects there were. A sample of 14 is version A. And it says that 20% survive. So to get 2 that survive, you'd have 14, 0.2, 2. Then even people that got this one right got the next part wrong. What is the probability that at least 3 survive? At least 3 means greater than or equal to 3. right? So to do that, you have to go 1 minus, well, let me put the intermediate step. 1 minus the probability that x is less than or equal to 2. So there were several common mistakes here. A lot of people just gave me this. They computed this probability. Instead of greater than or equal, they just did binom CDF and put a 3 in it. But that's the probability that x is less than or equal to 3, not greater than or equal to 3. So this then is 1 minus binom CDF at 14.2 and 2. And that answer is 0.5519 if you go to 4 decimal places. Okay? Other version is similar, different numbers. And the final answer should have been 0.3828. Okay, top of the next page is a central limit theorem for proportions problem. And those that recognized that generally did well on it, and those that didn't, there were a few people that got credit on this one, and because they used the binomial distribution. But if you're going to use the binomial, you can do it, but you got to convert from proportions into x's, because the binomial wants x's, right? But remember, when they did the central limit theorem for proportions, they said this is using the normal approximation to the binomial. So if you used the binomial here, you actually were more accurate. And there were a few people, but only a handful, that did it that way and got all the way through it correctly and got the right answer. But what you would do is say, well, if, let's see, version A says in the sample, or what's the probability that the proportion in the sample is greater than 0.26? You say, well, it's a sample of 500. 0.26 times 500 would mean you had x equal 130 successes, and then you do binom CDF to get 130. Okay, and the last problem with the tree diagram, it was clear that we didn't have enough homework problems over tree diagrams because an awful lot of people forgot even what a tree diagram was, right? So there are people that missed that part of it, which I intended to lead you to the correct answer on the bottom. They got the bottom part right, but didn't know how to do the tree. That's okay, it was not worth as many points. But I'll start the tree out, I guess, since there were quite a few. But our book draws tree diagrams from the top down. I did them in class a lot of times from the left to the right. It doesn't really matter. But when you are man or woman, and there were, depending on your version, 9 out of 15 and 6 out of 15 men and women. So I wanted those probabilities on the branches. So when it said write the probability above each branch, that's what I started. And so then on the next draw, if this one was a man, how many men are left? 8 out of 14. So you see how the numbers drop as you go through the table because you're sampling without replacement. Right? So then you fill in the whole tree. You'd have one more row, so you'd have 8 branches altogether. And the probability is just the product. One version asks about 3 men, the other one asks about 3 women, so it's just the product of all the probabilities along that branch. So this one, that last branch to be men would be 7 out of 13, so it's just the product of those 3 numbers. That's your answer to part B. Got it? All right. Well, anything else that you have questions about the exam, I will have the key to it posted sometime, hopefully later today, but if not by tomorrow or whoever reminds me first. Then it'll get up. All right? And then look at the key, compare to your test, and then come in and see me or email me or call me or something and get your questions answered. So I have mentioned, right, that the final is comprehensive. All right?
We just
So-
get one cheat sheet, or do we use all 4 in the exams? And then if it's
Just one.
Okay. Well, that's not
Just one. I used to allow all of the previous cheat sheets on the final, figuring out what the heck, but I found that people tend to study better if they have to consolidate from all that stuff and get it all onto one cheat sheet. So, I'm doing it for your own good. That's what your parents always tell you, right? Okay, so today we're going to do two sections, hopefully, although since I spent that much time on the test, I might not get through all, but we'll do section 8.2, and I'm going to go through it really fast and not do a whole lot with it, and leave it for you to kind of read on it. All it is how to get a T critical value instead of a Z critical value. The entire section is about that. And then we'll spend the most of the time today in section 8.3. So to introduce this topic, oops. I forgot to turn on the overhead, so that'll take a little bit to warm up. But to introduce this topic, last time we did confidence intervals for mu when sigma is known, right? Everybody remember this? But what about real research? Can you think of a time when you're trying to estimate the population mean? So you go out and you draw a sample, you collect data, and you use your sample mean to estimate the population mean, but you know what the population standard deviation is? You don't know the mean of the population, but you do know the standard deviation of the population? That's never really going to happen in practice. They teach it this way because the formulas are easier when sigma is known, and it's a good way to introduce the topic. But today, we say, okay, come back to reality and realize that when you're drawing samples from a population, you're not going to know any of the parameters. You're not going to know mu, you're not going to know sigma, you're not going to know anything. Right? That's why you're taking the sample. So, today what we'll do is, what if sigma is unknown and that's reality? Okay, well here's a little review. Remember that the 95% confidence interval that we had last time was X bar plus or minus, actually I put 95%, but I'm going to keep it in general, so 90 whatever. You have a Z critical value times what? Standard error of X bar. Right? And then these two pieces multiplied together, we gave that a special name. What's that called? Margin of error. And we used capital E for that. Alright? So far, I'll review. But now, what is the standard error of X bar? Okay, standard deviation of the population over the square root of n. Okay, here's the problem. What if sigma is unknown? Well, you just say, we're hosed. You can't do it. Well, what do you do when you're a statistician and you don't know something about the population, but you got this sample of people? What would you do? If you don't know sigma, what do you have to do? You got to estimate it. And what's your best estimate of sigma going to be? your best estimate of the population standard deviation, given that you have this sample here? What do you think? I ask this question like this every semester, and I always get the same silent, blank stare. It's like, I have to estimate something about the population from a sample. So whenever you get asked that question, your answer should be, oh, you just use the sample one of those. If you're trying to estimate the population standard deviation, you use the sample standard deviation. If you're trying to estimate the sample mean, you use the sample. I said it wrong. If you're trying to estimate the population mean, you use the sample mean. So whatever it is you don't know about the population, you stick in that same quantity computed from your sample. So we estimate the standard error of x bar with Sx over the square root of n. Okay? So here's the wrinkle that causes. If we wanted to know a z-score, and we wanted to know how far did our sample mean fall from the population mean, but I don't know sigma, and I put in Sx over the square root of n. If I had sigma over the square root of n, this thing would have a standard normal distribution. And we would use z critical values from the standard normal distribution. The problem is when you stick in Sx, Sx is a random variable, just like x bar is. So instead of a constant, sigma, on the bottom, I got a random variable on the bottom. Hey, more randomness means more variability. So we need a distribution. This thing is no longer z, it's t. It's a t distribution. T distribution with n minus 1 degrees of freedom. Okay, now that's a fairly new term, right? Degrees of freedom. I think we talked about that early in the semester. If you remember, the formula for Sx is the square root of the sum of x minus x bar squared over what? N minus 1. There's your n minus 1. That's why, because you're using this Sx in this calculation. So you have to use, instead of n, you use n minus 1. That's called the degrees of freedom. So this t distribution is very similar to a standard normal distribution, but it's a little shorter and a little wider to incorporate the extra variability. All right? So let's look at the slides and see what this looks like. So I don't know how well you can see that, but maybe I can zoom it up a little bit. Oops, that's not what I wanted to do. There. So the standard normal is this top one, and it's black, right? The t distribution depends on your sample size through this degrees of freedom. So if you have a really small sample, degrees of freedom are 3, what would the sample size be here? If the degrees of freedom were 3, what's the sample size in? 4, right? You're thinking I was doing some hard algebra problem. So this would be a really small sample of size 4, would have a t distribution with 3 degrees of freedom. That's this blue line. I think that's blue. Does it look blue? And notice that it's quite a bit shorter than the standard normal and quite a bit taller over here. So think about the critical value. Remember what the critical values are. How many standard errors do I have to go to get so much area in between? So for 95% confidence interval, what is my Z critical value? That was 90%. What did you say? 1.96. Good. Right? You should have those memorized. Either you memorize them or you write them on your cheat sheet. Right? So 1.96. So 1.96 is about right there. So under the black curve, 1.96, there's 2.5% of the area out there, right? 0.025. But what about under the blue curve? How much area would be out there? More or less? More. So in order to get it down to 2.5%, so I have 95% in the middle, I got to move further out. So my T critical values are going to be bigger than the Z critical values. So where do we get these T critical values? Well, here's one way you can get T critical values. And that is from a T table that's in the back of the book. And this is an excerpt from that table. So you'll see over here in the left column, degrees of freedom. And then at the top it says area in one tail. And then here's area in two tails. And notice that that's always just double, right? It's a symmetric distribution. So if I want 95% confidence, which column would I look at? Abby, I read your lips and you said it right. What did you say? What? No, you didn't say it right. Yeah, here. Yeah, gotcha. You did say it right. Area in two tails would be 0.05, so area in one tail would be 0.025. So for 3 degrees of freedom, like that one, we'd have to clear out to 3.18 in order to get 95% in the middle. Right? So what does that do to our confidence interval? So when sigma is unknown, let me erase under here, and let's change. So sigma unknown, let's change our formula. X bar plus or minus a T critical value instead of a Z times Sx over the square root of n. If I replace a Z critical value with a T critical value, what happens to my confidence interval? Does it get narrower or does it get wider? It gets wider because those T values are bigger, right? Now, does that make sense intuitively? If you're using an estimate of something you don't know, you've got more variability because your estimate could be bad, right? So to be as confident as you were before that you've got the true mean in that interval, you need to make the interval wider to have the same confidence because there's more variability going on, so I need to put more numbers in there as being plausible values. All right? So that is really all that's in section 8.2. Right, is the T distribution. But if you don't want to use this table, how can I get these T critical values out of my calculator? And here's the disappointing thing for some of you. Haley is one of them. Everybody that has the black TI-83 will not have this function on their calculator. And some of the TI-84s don't have it. But remember when we wanted Z critical values, what function did we use? Inverse norm. For a T critical value, guess what you're going to use? Instead of inverse normal function, it's inverse T function. So you're going to use inverse T. And the inverse T function, just like the inverse norm, it's area to the left, because it's a percentile function, area to the left, comma, degrees of freedom. So let's practice with this one we just looked up. Let's see if we can match that number using our calculator. what would I enter? Inverse T of I want the area to the left of the T critical value. How much area is in one tail? 0.025. So it's just like it was when we did the inverse norm. You take half the leftover area and plug it in. You're going to get a negative sign on your answer, and then you just ignore the negative. You could also enter 0.975 and get the positive one, but this one's easier, I think. And then 3 degrees of freedom. Tell me what that gives you in your calculator. Negative 3.18224. Right? I wanted one more decimal place than's in the table just to show that, yeah, we're getting the same thing rounding to 3 places. Okay? And 3 places of accuracy on a T critical value is plenty. That's what we used on our Z's. That's enough for a T. Okay. So the homework problems, I'm going to jump away from this section, but the homework problems will have you use this inverse T function or a T table to do 3 types of questions. They'll have a T, they'll have a T distribution, and they'll say, find all the T with this area to the right. So find a T that has, let's say, 0.12 area to the right. They'll make up some number. Okay, how do I find that T? My inverse T function wants the area to the left. So you do 1 minus the 0.12 and get 0.88 and plug it in. And they'll tell you the sample size. So sample size minus 1 is degrees of freedom. Then they'll have some where they say left of negative absolute value of T and right of absolute value of T. What in the heck is that saying? So they'll say area of 0.90 left of negative T, or actually be a small number like 0.10, area left of negative absolute value of T and right of T. Right, the T distribution is centered at 0, just like standard normal. So if they write it like this, what are they saying? Well, it's saying the area that's outside of what I just drew here has to be, and I didn't draw it very symmetric, did I? This area plus this area must be 0.10. Right? So there's 0.10 area that's left of this and right of that. So what's in the middle? 90. So if you can draw the picture, and all of those homework problems, I was looking at them yesterday, they all have part A, which of these graphs is the right graph for this? Then once you see the graph, you can figure out, okay, what do I need to enter into my calculator? Or what do I need to look up in the table? Right? So if you're doing it with the T table, if you were going to work this problem with the T table, then in this area would be 0.5 and in this area 0.5, right? So they add to the 0.10. So area in one tail is 0.05. If you had 4 degrees of freedom, you'd say, well, that's 2.132. And that's your answer. Okay?
So how do people with this calculator find out that?
I'm glad you asked that because I was going to forget to say. If you have the TI-83 or an 84 that's older and doesn't have the inverse T function on it, you have 2 choices. Learn to use the T table and forget it, or you can program the inverse T function into your calculator. That sounds horrible. God, I got to program a calculator. But it's actually pretty easy, and I've posted already out there for you on D2L the instructions to do that. Right? And then in the middle of your calculator screen, the black buttons, you'll see one that says PRGM on it or something like that.
Yep.
Program. Then once you've programmed it, it'll be in there. You push program, you highlight inverse T, hit enter, and it'll do it for you. Okay? So it's not hard to do, but some people are computer programming challenged, and so they don't want to mess with that. And I will have T-tables available for you during any test. Right? So you don't have to have that function to get by. Okay? So now let's look at section 8.3, and what we're going to do is we're going to take some data and we're going to do the computation like this by hand. But then we're also going to use the automatic function that's built into the calculator to do these T intervals, where the T critical value is automatically inserted and it's in everybody's calculator. It doesn't show you what that value is, but it's used. Right? So here we go. Well, yeah. I've already given you all this, so I'm just scrolling down to, I get to here. So what I have here is, if you remember last time we combined two people's worth of data to get a sample of size 10. So I'm doing a similar thing here. This is from your data, only it's female heights instead of pulses. Okay? And I just took the first, I believe I took the first 10 females that were in the data set. And here are their heights. So I want you to take this data and put it into L1. Okay, so for purposes of the video, I will read them off, but first one is 62, second one is 64, third one 64, then 68, 62, 66, 63, 65, 63, and 61. Okay? Then when you get those entered into the list, then the next thing I want you to do is to do one var stats and give me the mean and the standard deviation. And I'll write those here. Actually, let me slide this over. What'd you say?
For 63.8.
63.8. Okay. And then SX?
2.09.
2.09. Give me one more place.
7, 6. So
It'd be an 8?
Yeah, 8.
Okay. 2.098. Okay? So I don't know if you remember, and I don't think I remembered to bring it. I could pop it up, but what the female height population mean was and standard deviation. I remember the standard deviation was about 3. So this is a little bit of an underestimate. Right? So that's what I was talking about. When you use an estimate of the standard deviation, you could be off. So we know that for all 365, well, I guess we didn't have 365 females, but 180 or whatever it was, the standard deviation was about 3. Okay? And the overall mean of all the females was about 65.2 inches or something like that. So it was a little above 65. So our sample mean is a little bit of an underestimate, and our standard deviation is a little bit of an underestimate. But let's use this to produce a confidence interval. So that confidence interval, it's still written on the board over there, right? So I'm just going to enter the numbers. So 63.8 plus or minus some t critical value that we need to look up, and then times the standard deviation divided by the square root of the sample size. So we just need that t critical value. Well, now you know how to use your inverse t function. Go for it. Give me that t critical value, and if you don't have the inverse t function, oh, they don't have 9 degrees of freedom on this table. Darn it. Use the back of your book to look it up. Caitlin?
How'd you know to use 9 degrees of freedom?
Good question. Did I erase it?
Oh.
Yes, I did.
N minus 1.
It's n minus 1, exactly. So sample size is 10, so degrees of freedom is 9. It's always just one less than the sample size. I've always kind of wondered, and I guess it's just historically it's always been done that way, but why don't they just put sample size? Right? Why do they make me take 1 off the sample size and then look it up? Just put sample size instead of degrees of freedom on that left column, but that's just what they do historically. Right?
What confidence interval?
Let's do 95%. Sorry, I should have said that. The t-table, if you have your book, the t-table is in the back cover of the book. It's this one. This one over here is a chi-square, which we'll get to at the very end of the semester. But the excerpt you were looking at is the first 8 rows of this table. So for 10 degrees of freedom, or 9 degrees of freedom, if you have your book, look it up from there. For 95% confidence, remember you're looking in the 0.5 in 2 tails or 0.25 in 1 tail column, down to 9 degrees of freedom. And what number do you see there, or what did you get out of your calculator? Who's got the critical value? Hello? 2.262, and that matches exactly what's in the table. 2.262. So 2.262, I'm going to put a little arrow and say from t-table in book or inverse t function. Okay, so now you've got all the numbers. Do it in your calculator. Start with the minus sign. Doesn't matter which you start with, but do one of them. Type it all out. Hit enter. And then if you, on your calculator, if you push second function enter, it'll pop up the last thing you did. And you can arrow to the minus sign and change it to a plus sign, and you don't have to type everything back in. Yes? It's always the area that's left. I'll let you use my calculator. It's always the area that's left of the critical value you want. And so, slide this. If you want 95% confidence, draw a little picture. You'll find that you don't have to draw the picture after you do a few of them. You can just kind of visualize it. But if I want 95% confidence, that means I want a negative t and a t that have 0.95 in the middle. So then how much is left over into each tail? 0.025. And so you just enter that number. So it's the area in one tail that you put into your inverse t function. Okay, so who's got the lower bound of this interval for me? 62.219? 30. I like that. Right? And to the nearest hundredth of an inch is overkill. So you don't need like 5 decimal places on it. Okay, and then what's the upper bound? 65.30. That doesn't seem quite right to me. It is right?
Yeah, that's right.
I'm surprised because this is not Oh, I guess that makes sense. Yeah, it's at 0.8, so you're going 0.5 below and 0.5 above to the next one. Okay? So, now, the most important thing here, in my opinion, is not the numbers, but what are these numbers telling me? What's the interpretation of a confidence interval?
Or you predict the confirmation.
Good. And the way I want you to say that, start this sentence. So on the text, I will say, compute a 95% confidence interval and interpret it. So the interpretation should start with, we are 95% confident, and then say what Jody said. We are 95% confident that the true population mean, or you don't have to say true, but the population mean is contained in that interval, right? So we are 95% confident that mu, which is the population mean height, is in the interval. Okay? Then you can use that interval to make inference. Maybe you've got some different population of women, like Japanese women, and you do a confidence interval for Japanese women. And you say, is there evidence that Japanese women are shorter than general world population? If the confidence interval excludes the population mean for all countries, then you'd say, yeah, I have evidence, right, that they are less. But if it overlaps, then you say, oh, no, they might be less, they might be taller. It's hard to say. Okay? Now, you've got 30 seconds to do this one more way. On your calculator, push the stat button, go over to tests, and go down to T interval. So stat, tests, and then T interval. And when you hit enter, you'll see at the top it says INPT. And that's for input. And then it says data or stats. If you have data entered into a list, the easiest thing to do is select select data, and then the screen will change and it will ask you, okay, what list is your data in? So do it that way. Since you entered these into a list, select data, but let me finish that thought. If you don't, if you're reading a problem and all they said was, well, the sample mean is 63.8 and the sample standard deviation, then you just select stats and it'll let you enter those things. Okay? So you could do that here because we already have figured them out, but I want to show this also. So it'll say, what does it say, like data list or
List.
just list? So it'll ask for list, put L1 or wherever you put it, and then frequency, and leave frequency at 1, and then, yeah, sea level, right? So sea level, enter 0.95, and then calculate. You should get this same interval at least rounded to 2 places. Everybody get the same thing? All right. There you go. On the homework in the Hawk system, most of the questions over 8.3 will say, what's your best point estimate? That's part A. And so that's just X bar. And then it'll say, produce a confidence interval. Just use your T interval function. You can do the confidence interval. And that's all you need to do. Okay? If you get it wrong and ask for help, they're going to walk you through this whole formula, but it's built into your calculator, so you should be good. We will see you Friday. All right.